I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will briefly discuss about the activation function which is used in the neural networks. First, we should know what is an activation function. An activation function in a neural network is a mathematical formula applied to the output of a neuron to decide whether that neuron should be activated or not. It introduces non-linearity into the model, which is critical because real-world data is often not linearly separable. After a neuron processes the input data by computing the weighted sum and bias and adding the bias, the activation function transforms that sum into a new value. This value then passes forward to the next layer. Without activation function, a neural network, even with many layers, would collapse into a simple linear regression model which lacks the capacity to solve complex problems. And in this case, we are going to take the inputs. X1 is 0.8 and X2 is 0.4. Weights are each input. We have discussed in the previous lecture. Each input is associated with one weight value. For X1, the weight value is 0.5, or X2, W2 is given by 0.7, and bias is 1. And bias is always multiplied by the input, X is equal to 1. The raw sum is given by the weighted sum, Z is equal to 0.8 into this 0.8 and 0.5, that is multiplied by here 0.8 into 0.5 plus 0.4 into 0.7 and plus 0.1 into 1 is equal to 0.78. If you are using the ReLU function, ReLU of 0.78 is 0.78. And using the sigmoidal function, we know the formula 1 plus e power minus z. The minus z is this value. If you are substituting 1 divided by 1 plus e power minus 0.78, we are going to get 0.685. So the neuron outputs 0.685 instead of this 0.78. This transformation ensures that values are kept between 0 and 1, the preparing the signal to be passed to the next layer in a controlled way. Next, why are activation functions are important in neural network? Activation functions are essential because they allow neural networks to learn and represent complex relationships. They enable networks to draw nonlinear decision boundaries, which are needed to distinguish between different classes when the data is not linearly separable. Without them, the network cannot perform better than a straight line classifier, regardless of how many layers are added. Different activation functions like ReLU, TANH, and the sigmoidal helps capture various types of nonlinearities present in input data. And if you are taking one example, practical example, XOR problem, take the XOR gate as an example. The XOR function outputs when it will be giving it as output 0, 0, 0, 1, 1, 0 and 1, 1. For these cases, output is 0, 1, 1, the output is 0, and for these two cases, the output is 1. So the XOR function outputs 1 only when the input differs either 0 or 1. This pattern cannot be learned using a single layer perceptron with a linear activation because no straight line can separate the output classes. This we have seen, it has been separated with the that is here two lines. No straight line can separate the output classes. However, by introducing a hidden layer and using sigmoid or TANH activation functions, the neural network gains the ability to create curved decision boundaries. So the curved decision, this may be like this. This allows it to learn the XOR logic successfully. This classic problem proved the necessity of nonlinear activations for neural networks to be useful. Next, the role in learning and backpropagation. theory. Activation functions must be differentiable so that gradients can be computed during, it must be, this is the main first condition. What is the necessity of that should be differentiable? Hence, the gradient can be computed during propagation, back propagation. Back propagation is the method by which neural networks learn. It adjusts the weight by computing the gradient of the error with respect to each weight. If the activation function produces very small gradients as sigmoid does for so large positive or negative input, the learning slow down, a phenomenon known as vanishing gradient problem. Vanishing gradient problem. This is very, very important property in this case. Functions like ReLU and leaky ReLU helps avoid this problem by maintaining non-zero gradients even for large input values. Next, use of output layers. In the use in output layers, in the final layer of the neural network activation function transforms the raw output into interpretable predictions. For binary classification tasks, the sigmoid function is commonly used to convert the output to a probability between 0 and 1. For multi-class classification, the softmax function, multi-class, very, very important two-mark question. Multi-class problem, softmax function is used to produce a probability distribution over all possible output classes. These output activations are not just mathematical tricks. They determine how we interpret the model's answer and how loss it is calculated during training. And if you are taking the example for this, the binary classification task determining whether an email is spam or not, spam cases, spam or not, the sigmoidal, the final uses of a sigmoidal function. If the raw output from the final neuron is 2.0, applying sigmoid value 1 divided by 1 plus e power minus 2 is equal to, we are getting 0.88. The probability, that meaning the model predicts the 88% probability for that the email is spam. In multi-class cases like digit recognition means 0 to 9, softmax is applied to output like 2 that is 2,0, the values 0.01, 0.0. This helps us interpret the prediction as digit 2 with 85%, digit 8 in this case with 85% confidence. And we'll see the various types of activation functions, various classification. The first one is the linear activation function. The linear activation function, the formula for this is given by f of x is equal to whatever the x varies, the output is also f of x. And the graph of linear activation function is, this is the graph of linear activation function. If x varies, f of x will also be varying. So that we are writing it as f of x is equal to x. The graph of linear activation function is a straight line passing through the origin with a slope, the slope is equal to 1. The function outputs exactly what it receives, and here this function exactly what receives an input, meaning it does not transform the data in any nonlinear way. It won't transform. While it can be useful in regression tasks where continuous output is needed, using this function in hidden layer is problematic. That's why, because stacking multiple linear layers results in an equivalent single layer transformation, effectively collapsing the deep network into a shallow one. This lack of complexity, the lack of complexity makes the linear function unsuitable for learning intricate patterns and representation in deep learning. Next on is the step function. The step function, if you are taking, the output is if the x value weighted some value is less than 0, output is 0. If it is greater than or equal to 0, the output is equal to 1. The step function graph displays the sudden jump. See here, below 0, 0, and then sudden jump will be there. And it remains at 0 for all negative inputs. All negative inputs, the value is 0. And see, after the 1, the value is this binary behavior makes it resembles a digital switch. Historically used in early neural networks like the perceptron, it has since fallen out of favor due to its non-differentiable nature at the threshold, that is 0, the zero gradient elsewhere. These properties prevent the use of gradient descent, making it incompatible with the modern learning algorithms like backpropagation. Though conceptually simple, it is largely absolute in today's neural network models. Next is sigmoidal logistic function. The sigmoidal function graph, see here this function we have seen it in the previous lecture, 1 divided by 1 plus e power minus x. This is the graph for this, so like root nature. And in this case, it smoothly transition from 0 for large negative inputs to 1 for large positive inputs. This behavior is ideal for binary classification problems, especially at output layer where the output can be interpreted as probabilities. However, the sigmoid has two major issues. What are all the major issues in the sense? The first one is it has two major problems. First, it is not zero-centered, which can slow down trained. That is, second one is it suffers from the vanishing gradient. That is the main drawback. Vanishing gradient. Second one is the non-zero centered problem. And especially when inputs are in the saturation zones or from 0. Despite these issues, sigmoid remains useful in specific contexts, especially for probability modeling. Next, tan H activation function. This is given by e power x minus e power minus x divided by e power x plus e power minus x. These are all weighted sums. The output would be minus 1 comma or plus 1, and it is being used in the, it is better than the sigmoidal in the hidden layers. How we are calling it as the better than the top. This is the graph. So this is the sigmoidal. This is here the sharp curve was there. But zero-center nature helps balance gradient update and stabilizing learning. Tanh is often preferred over sigmoid in hidden layers for these reasons. However, it still shares the drawback of slow learning in deep network due to saturation effects for very large or small inputs. So these are all the drawbacks. ReLU function. What is the ReLU in the sense? Rectified linear unit. It is given by f of x equal to maximum of 0, x. The graph is given by, so below 0, the value is 0. After then, it will be sharply, it is increasing. If f of x is equal to x, linear and positive inputs, output is equal to what? This output is equal to input in this case. But below 0, the value is 0. This piecewise nature allows it to be both simple and effective. ReLU is currently one of the most widely used in activation function in deep learning because it avoids the vanishing gradient and problem for positive inputs and is computationally efficient. However, for negative inputs, the gradient is 0, which may cause neurons to die during training, and meaning that they stop updating. Despite these limitations, ReLU benefits for overweight its drawback, especially in convolution neural networks. Next, leaky ReLU. This is the ReLU function. This is the leaky ReLU. It is given by maximum of alpha x comma x. Alpha value would be 0.01. It is used in the variations of the ReLU that allows the small gradient for x is less than 0. The graph is linear. So small variations in the negative side. The graph is linear for positive inputs and slightly negative for negative inputs. This tweak addresses the dying ReLU problem by maintaining a small non-zero gradient when the input is negative, allowing neurons to stay active and because of this gap C, active and continue learning. Leaky ReLU improves learning dynamics in deeper networks while maintaining simplicity and efficiency. It is preferred choice when encountering the issue of inactive neurons during training. Next, parametric ReLU. It is being used in the, it is like a build on leaky ReLU by making the slope for negative inputs, here slanting, and learned parameter rather than the fixed constants. In the graph, it means that in the negative region, slopes can adjust based on training data. This added flexibility allows the network to adapt more closely to the data's distribution, potentially improving performance in complex models. By letting the network learn the optimal activation concepts, pre-ReLU, that is Parametric ReLU can outperform both ReLU and leaky ReLU in certain tasks. However, it does introduce small increase in computational cost, parameter complexity. That is the main drawback. Next, ELU in the sense exponential P ReLU means parametric, ELU means exponential ReLU linear unit. The exponential linear unit behaves like a ReLU for positive inputs, but for negative input, it curves smoothly and asymptotically approaches here in infinity. There is a plus infinity or minus infinity. Alpha is the hyperparameter in this case. Here, alpha is the hyperparameter. In this case, typically 1, the graph shows the smooth curve in the negative domain and the straight line in the positive domain. See here, positive domain. And the smooth transition reduces the bias shift and brings the average activation closer to 0, accelerating training. ReLU also avoids the dying neuron problem better than ReLU. However, its exponential terms makes it more computationally intensive, which can be downside in large scale networks. Next network is the Swiss. This function is given by x into sigmoidal x. So its graph shows that the gentle curve here that it is only varying here, straight negative inputs, outputs, and grows almost linearly for positive values. Unlike ReLU, Swiss does not abrupt zero out negative inputs. Abruptly it has not been zero, which allows a richer gradient flow and better learning in deeper network. Its flexibility helps models escape local minima more effectively, leading to superior performance in many deep architectures. Though slightly more complex to compute than ReLU, its benefits is expressiveness and a smooth gradient flow makes it powerful modern activation function. Next function is MIS. It is given by x into tan h of ln 1 plus e power x. The smooth non-monotonic monotonic activation function, it is defined as this. Its graph is smooth. See here, smooth and allows small negative outputs, which grows pattern that combines the best Swiss and tan h. MIS enhances learning process, learning by maintaining smooth gradients and introducing non-linearities that improve generalization. It performs particularly well in computer vision, task, and deep architectures by offering better features richness. Although it is more computationally expensive, its robustness and self-regularizing nature makes it one of the most promising new activation function. Next, this is the MIS function. Next one is the softmax. The softmax function is given by e power zi divided by summation of e power zj. And softmax does not apply to an individual values like other activation function. Instead, it transforms an entire vector into a probability distribution. The graph shown is for a bar chart illustrating how softmax convert input logics into values that sum to equal to 1, making it ideal for multi-class classification. Each output's magnitude reflects the relative strength of that class compared to others. It introduces the competition among output neurons, pushing the largest value toward 1 and other toward 0. This probabilistic interpretation is essential in classification tasks like image labeling, where we need a single best guess among multiple categories. And the another function is the softmax. The softmax only I have told. The final one is the max out. It is given by max of, this is the weighted sum B1 and W2 transpose X plus B2. Max out is the general purpose activation function that outputs the maximum of 2 or more maximum value. So if suppose if I am having 5,7 max of, I'll be selecting only 7. So max of 2 or more linear functions. Its graph shown shows the piecewise linear curve within a bend rather than smooth transition. This allows max out to approximate any convex function, providing exceptional flexibility in learning complex data distributions. Unlike ReLU or switch, max out has no saturation in zones, and each neuron effectively learns its activation shape. The trade-off is computational cost. Each neuron requires multiple weight vectors, which increases memory usage and training time. Max out is powerful, but typically reserved for tasks where model performance justifies the extra complexity. Next, coming in, this is the table. So for all the functions, the output range will be like this and used in regression output. A step is used theoretical purpose. So the gradient issues is there or not, vanishing occurs or not. So this is the table of the summary of the table. And coming into the summary, the why study activation function. Studying activation function is essential for anyone working in neural network because they are gateway through which information flows and learning happens. They allow network to move beyond linear assumptions to model complex nonlinear relationships in data and train effectively through backpropagation. The choice of activation function can determine the difference between a model that learns quickly and one that fails to converge. Whether it's a ReLU or a soft for deep learning convolution layers, sigmoidal or binary output, or softmax for multi-class probabilities, activation functions are present in every successful application of neural networks, from medical diagnosis and to self-driving cars to a natural language translation and fraud detection. Without them, neural networks would not be able to perform intelligent decision making at all. Hope everyone understood about the basic concepts of activation function. The remaining things we'll discuss in the next lecture. Thank you.